And this is 3.5, connection-oriented transport, particularly the TCP protocol. So in this particular section, we're definitely going to talk about the RDT implemented in TCP. Now, provided the background, very extensively in 3.4, you should be able to understand TCP's implementation of RDT, TCP's design of RDT. Now, in addition to the RDT in TCP, we are also going to talk about the packet format of TCP. And that is what the segment structure meant here by the textbook authors. And then there are two minor functions, but necessary functions in TCP. One is called the flow control. The other is called the connection management. And this is the overview. TCP we know already. Just like UDP, it's what? End-to-end process-process communication. So end-to-end there can also be referred to as point-to-point communication. We have a sender process and a receiver process. Now, in this connection here, what we're doing is to do reliable and in-order data transmission. Now, what's a little bit unusual when we talk about TCP is this. Instead of earlier, when we were talking about the general principles of RDT, we are counting the data by what? Packets. Packet 0, packet 1, packet 2, packet 3, so on and so forth. But in TCP, we count data alright, but we count the data by the bytes. Byte 0, byte 1, byte 2, and so on and so forth. So that connection here, when we are passing data around, we are actually passing a stream of these bytes. Right? So there's no more message boundaries, or there's no more packet to packet separation. Right? And last, this is actually telling you ahead of time that TCP's reliable data transfer is doing this, the pipeline-based RDT, so that we have a window size there where the size n is definitely larger than 2. And so we could have multiple packets in transit so that the utilization of the connection there can be higher. Okay. Now, what we don't know quite yet is this window size is also used not just for reliable data transfer. Later on in section 3.6 and 3.7, you will also hear it's also for the congestion and flow control. Okay, so there's going to be a window size for flow control, and the window size for RDT is also used for congestion control. And conveniently, in flow control, what's being done is the receiver will every now and then tell the sender, hey, you might want to slow down or you might want to speed up depending on how much the buffer space is occupied at the receiver side. You see, what happened at the receiver end of the TCP is this. Data will come in continuously from the sender. Data will be extracted and passed up to the application layer process. So there's an incoming rate and there's also an outgoing rate. When the outgoing rate is slow, incoming rate is fast, then you see the buffer space is quickly exhausted. Okay, so at that point, receiver tells the sender, hey guys, slow down. All right. Now, the other way around, if the buffer space is very empty, then telling the sender, feel free to send more. So flow control there. Okay, mainly allowing the receiver to tell the sender, hey, slow down or speed up, such that there's no congestion occurring at the receiver side. Because if the incoming rate is high, outgoing rate is slow, over time, when the buffer is exhausted, the incoming packet, incoming data will be what? Will be dropped. Okay, so delay long, and you see also data loss there, right there at the receiver. So this is to avoid also congestion, but it's a bit weird. It's actually to avoid congestion at the receiver side, not quite in the middle of the internet. Okay, so when I say in the middle of the internet, I actually meant congestion in the core of the internet. Sender process, receiver process is what? At the end of the internet, at the edge of the internet. So flow control there is to try to control the end processes such that there's no packet drop at either end. Congestion control, on the other hand, is to control such that there's no packet drop or congestion in the middle, in the core of the internet. And TCP, being connection-oriented transport layer service, is sending some messages at the beginning before data can be transmitted. So there are some handshaking being done right before the data exchange. And these handshaking messages are there to set up the initial states of the sender and receiver. And that is called the connection management part of TCP. Last but not the least, there's a mindset change here in a TCP connection. Data traveling in a TCP connection is now full duplex. What I meant by that is the data flow is going, bidirectional. Okay, so two processes or point-to-points, will be sending data this way as well as this way. Now, why is this a major mindset change? If you recall in 3.4, when we were talking about these reliable data transfer mechanisms, we always say what? This is the sender side of RDT, and this is the receiver side of RDT. What we are saying there implicitly is also, this is data sender side of RDT. This is the data receiver side of the RDT. Data receiver there, receive data. It transmits something as well, but it's transmitting only what? The feedback messages, the ACK messages. The receiver there does not send data. So TCP here you see being more general. Data can go either way. So the two processes will be implementing both the sender and receiver finite state machines. And the last bit is this. MSS, a special term that is referring to this, the maximum segment size. If you recall, a packet at the transport layer is called a segment. So maximum segment size is essentially the maximum packet size. Okay. In reality, in actual TCP implementation, we're still sending data packet by packet. But the sequence number we'll be checking to do reliable data transfer is now counting the bytes of the data, not the packet numbers of the data. TCP Signal Structure, aka the packet format. It does look a bit complicated, definitely more complicated than the UDP packet. If you recall, in UDP we do have these fields: source port number, destination port number, as well as the checksum. So all these are what called the header fields. So in TCP packet, the header part is substantially larger. While the data part, it's still variable lengths that could be large, could be small. So the overall structure in TCP packet is actually very similar to UDP, two parts, header and data. The main difference is where? The header part. So some of the header fields repeat itself. We see source port number and destination port number as well as checksum also in TCP packet header. But what else in the UDP packet header that we don't have or we do have in TCP's packet header? And here's UDP's packet format. So we do see source port number, destination port number, checksum. And what else is in UDP's packet header? The length. So that is the entire packet size, including the header as well as the bytes in the segment. So data and header together, in this field, the lengths. And do we have lengths here in TCP's packet header? Well, if we look around, something slightly similar. It is lengths. So LEN is actually short for length, but it's only the length of the packet header. So this part versus UDP's length, quite different. Semantic, very different. So UDP's length actually talk about the entire packet size, but Length here is only covering the first part of the entire packet structure, the header length. Do we have length in TCP's packet header? We actually don't. The thing that we have the closest is this, the header length. So the length in TCP packet header counts only the size of the TCP packet header, while the length in UDP's packet header counts the entire UDP packet. Given that we're already talking about the header lengths, why don't we talk about these special bits, special flags in the TCP packet header? First is the A flag. So this is called the ACK flag as well. When it's turned on, when the ACK flag is on, that's indicating that the acknowledgement number here is actually valid, meaning that the sender of this packet is trying to tell the receiver that it's trying to acknowledge certain bytes being received. And these three R, S, and F bits, they are there to indicate packets being used to do connection management. So for example, SYN here, the SYN packet is to set up connections. The FIN packet, which is Latin for the end, conveniently, is to tear down a connection. RST, or the R bit here, means reset, that is to re-establish the connection, to re-initialize certain parameters between the sender and receiver of a TCP. And P bit. P stands for push, that is to push data now. So this is to actually pass the data out as soon as possible, but it's generally not used. Just like the U bit, this is urgent, so this is indicating that whatever data is here is urgent. So pass it out through the network or to the application layer as soon as possible. So you see urgent, the purpose, and push, somewhat similar. The ambition of the network engineers much early on is also that hopefully a data network or the internet can also allow urgent data being sent, just like we could make it 911 call, or in Taiwan 110 call to get police's attention or the fire department's attention as quick as possible. But unfortunately, the way the internet is designed is just not very good for urgent, critical data transmission. And we said that these are not used, so there are a number of bits not being used. But the fact is actually there are two more bits being used. It's called the C bit and the E bit. Now these two bits are not really for reliable data transfer service, not for connection management purpose. They are actually there for congestion control. But it's not quite the congestion control implemented in TCP though. It's just that the engineers are expecting later on TCP's congestion control can be extended together with the core of the internet such that we could do better control. So there will be two more bits we'll have to talk about, but it will be at the end of chapter 3. And that takes us to the urgent data pointer. So this is actually working with the urgent bit. When the urgent bit is on, then the transport layer of TCP is going to look into this pointer and then grab whatever the data that's here indicated by the pointer. So this data here will be extracted and passed out as quick as possible. And receive window here. This is the window size for the flow control. If you recall earlier in the overview, we say flow control is for the receiver to tell the sender, hey, slow down or speed up. And when the slowdown is to be communicated, receive window here will be a small number. If the receiver wants the sender to speed up, the receive window there will be larger. And the last two fields in the header are these. the sequence number as well as the acknowledgement sequence numbers. So these are exactly for the reliable data transfer purpose. But keep in mind, we're now counting the bytes, okay, not packets. TCP sequence number and ACK numbers, these are very important fields. Let me elaborate more here. First, the sequence numbers. So what the sequence number says in the packet header is to tell you this: the byte stream number of the first byte among all the data bytes in the packet. So, but what is the byte stream number? Yeah. Let me explain. This is the original message, which can be really large, generated by the application layer process. Now, as it's pretty long, right? Each byte can be indicated in sequence in byte stream number. So this is byte 0, byte 1, byte 2, byte 3, byte 4, and so on and so forth. So these numbers, these serial numbers, are the byte stream numbers. So when such a message arrives at the transport layer, the TCP sender is going to what? Break them down into smaller parts. Let's assume that in the first segment, it contains only 3 bytes of the data. So in the header here, the sequence number is going to be what? Oh, the byte stream number of the first byte of data, which is 0. For the second packet, in the header sequence number field, what should be the value? It should be the byte stream order of the first byte of all the data, right? So 3 here. Okay, so that's what sequence number meant. And it tells you where the first byte of this data packet is in the original message. So we could track whether all the bytes in the original messages are being transmitted successfully. Second, the acknowledgement number. Now to explain this, let me tell you TCP implements. Just like go back in, cumulative X. So that number there, based on your knowledge of go back in, should indicate what? The last byte of all the data received correctly at the receiver and in sequence. But, well, it's actually not quite. So TCP's acknowledgement number is actually counting 1 byte further. So it's the next byte the receiver is expecting. So that number is the number of the next byte the receiver is expecting. Therefore, it will also be the what? The sequence number of the next data packet coming from the sender. And with that said, many of you will probably guess that TCP's reliable data transfer mechanism is similar to go back in. You are actually correct. So let me borrow the diagram that I've been using to explain the sender side behavior of go back in here. The only difference is just that previously, now each rectangle indicates a packet. But now we are counting bytes instead of packets. So each of these are what? Bytes. So we have green bytes, yellow bytes, blue bytes, and gray bytes. But similarly, to go back in, the green bytes are what? The bytes that are already sent and acknowledged. Yellow ones are the bytes sent and not yet acknowledged. Blue bytes are those usable, so if there are more data the application layer process wants to send, we could now turn these blue ones to yellow. So, usable but not used. Gray ones, not usable because it's what? Outside of the window size, outside of the window limit. Now, the sender generates a data packet. What's going to be in the sequence number is what? The first byte of the data and the byte stream number of it. And if an acknowledgement is coming back to the sender, acknowledging this packet, the acknowledgement number here is going to indicate what? The byte stream order of the next yellow packet. So this first one here is going to turn green. Yeah, so ACK number here is the first yellow next. And the last bit here is again about TCP's RDT being very similar to go backend. So if you recall, go backend's receiver, when it receives out of order packets, what does it do? It drops all the out of order packets. Now that is actually a wasteful use of network bandwidth, isn't it? So TCP here allows a bit more flexibility. The programmers themselves can decide whether to buffer the out of order packets or to drop them. Now let's exercise what we learned about the TCP sequence numbers and ACK numbers using a simple telnet scenario. The setting is this. We are here at host A. We've already started the terminal and it's connected to the remote machine, host B. So what happened in the telnet is this. When we hit C, a key locally, okay, so user type C, what happened is this. Host A sends a byte, that character C, to the remote machine. Now the remote machine is going to receive this and see what to do with it. Now, because it's a very straightforward character C, not like escape or control C, therefore, what it does is going to be simply echo back the character C to the local host. So host A here will receive the echo C and then display on the local terminal. So once again, host A here has 1 byte to send. Host B here has 1 byte to send. And that's the scenario. Now, the 1 byte of data generated by the telnet process. As soon as it arrives at the transport layer, we're going to add header to it. So sequence number, ACK number being added to it. And the data is simply a character C. Now, when this packet arrives at host B is going to what? Yeah, echo with the same character C. And in the meantime, acknowledge receipt of the data packet earlier. Right? So what will be the sequence number and ACK number will be generating? Well, we send 1 byte of data. What should be the sequence number there? Well, go back here. The ACK number is indicating what is the next sequence number. Yeah, the sender of the ACK packet is expecting. Therefore, sequence number we know should be 79. Now, what should be the ACK number here? Well, ACK number is what? The last byte received and then counting further by 1 byte. What is the last byte received? Yes, 42, because there's only 1 byte. And counting further, yeah, we say ACK 43, and this is also host B telling host A what is the next data byte expected. And therefore we see the next packet coming back from host A, sequence number 43. But host A here is not echoing C anymore. All it needs to do is to what? Acknowledge receiving this packet. Right? So ACK packet needs to be what? Last byte received by host A, which is 79 because there's only 1 byte. And counting further by 1. Therefore, we get 80. So you see, quite obviously, in order to find out what is the next sequence number, look at the packet coming the other direction's ACK number. In order to find out what is the ACK number, look at the packet sequence number coming the other direction. Similarly, sequence number here, look at the ACK. The ACK number, look at the sequence of the last packet coming the other direction.